Okay, we have some data for our balloon rockets, where we have the circumference of the balloon to show just basically how big it is. It's not going to be involved directly in a calculation. We have the distance of the balloon traveled, which should basically be 8 meters to go across from one side of the classroom to the other, as long as it pretty much made it all the way across. And the time it took in seconds to cross that 8 meters based on how big that balloon was and how much air it was blown out. Okay, so we're going to use the time it took and the distance traveled to try and kind of calculate roughly what the acceleration of the balloon was, and then use that to figure out the force on the balloon. So let's go down here. Okay, so we're going to look at our smallest balloon first, one with the smallest circumference, and that's going to be for both of these questions here. This is going to be the small balloon. Okay, so we want to plug in the distance and the time to figure out what this acceleration is. So this A is our acceleration. And it's going to be equal to 2 times our distance divided by our time squared. That should be our average acceleration. So if we go up here, the smallest balloon I had was this 29-inch circumference balloon. Yours might be the first balloon, it might be the last one, it might be somewhere in the middle. It doesn't really matter as long as you pick your smallest balloon. Okay, so the distance was 8 meters traveled, and it took 2.14 seconds to get there. So let's scroll this back down. Okay, so the distance traveled was 8 meters. And again, it should basically be 8 meters no matter what, as long as it's making it all the way across. Okay, let me see if I can get a darker color of yellow. That'll show up better. That's a little better. Okay, and then the time it took for this small balloon was 2.14 seconds. Okay, so in order to calculate the acceleration, we need 2 times this 8 divided by 2.14 squared. Now, there's two ways you could do this in your calculator, whether you want to use the exponent or not. So I'm going to first show you how you can do it with the exponent. So I'm just going to go to my Google calculator here. And get that toolbar out of the way. Okay, so I'm going to take 2 times 8 meters and then divided by, okay, I'm going to do my time, which was 2.14. That's kind of bothering me. I'm going to get rid of that mouse pointer there. That's a little better. Okay, 2 times 8 divided by 2.14, and I want this 2.14 to be squared. So over on the left side here, I have this little x with a little y up there. That little y is going to be our exponent. So if I click this now that I've typed in 2.14, that's going to be like where the x is, and then I'll be able to type a number in where the y is. So if I click on this, it says, hey, what do you want that number up top to be? What do you want that exponent to be? So I want it to be 2. I want it to be squared. So now I'm taking 2 times 8 divided by 2.14 squared. So now if I hit equals, that is my acceleration, 3.49-ish if we round it to like 2 decimal places. So I'm going to jump back over to here. So our acceleration is going to be about 3.49. Our unit for acceleration is meters per second squared. So how many meters per second speed it's changing per second. Meters per second is meters per second squared. Now, if you don't have a squared button on your calculator, you can't figure out how to use it, there's a safer way you can do it. It just takes a little bit more work. When you take something squared, it's basically like doing the same thing twice. So if I'm dividing by something squared, I'm basically dividing by that same number twice. Or if I'm multiplying by something squared, I'm basically multiplying by that same number twice. So in your calculator, if you take 2 times 8 divided by 2.14, and then divided by 2.14 again, oops, 14 there, and then hit equals, it should give us the same answer, about 3.49. Hey, and it does. Cool. So either way works. Whatever is more comfortable for you, whatever your calculator works best with, and you can do it either way. So whether you take 2 times 8 divided by 2.14 squared, or you write this out as 2 times 8 divided by 2.14 divided by 2.14. The answer should come out the same. Okay. Now, you'll want to plug in your time and your distance if you have different numbers than I do. This is just kind of a sample calculation, just to kind of give you a heads up on that. Okay. Now we're going to use this acceleration to figure out how much force there is on average on this balloon. So our force should be equal to our mass times our acceleration. So F equals m times a. We're looking for the force, so force equals. The mass of our balloon is going to be kind of approximated. It's hard to get the mass of a balloon by just setting it on a scale because it's kind of buoyant in the air. So I ran some numbers, did some calculations, and this is about the mass of a small balloon that you would use in the lab when it's full of air. So if we take this mass of the balloon, this small balloon, times our acceleration of 3.49 meters per second squared, okay, or whatever your acceleration was, we're using the same number down here. All right, we just multiply those numbers together and then we'll get the force. So really, this part up here was the hard part. This part down here is pretty easy once we have the acceleration. So if I take 0.00527 times this 3.49, I should get my force in newtons. That's our unit of force, is newtons. So let's do that. 0.00527 times, whoops, let's backspace that, times, I'm going to do 3.49-ish. That's going to be equal to about 0.0184 if you round this up. So 0.0184 is what I'm going to put here. 0.0184 newtons of force are acting on this balloon, which is not a lot. It's not a lot of force. So your balloon is pretty light. It doesn't take a whole lot of force to really get it moving. Heavier objects would need more force to get them moving the same way as a small object being moved at the same rate of speed increase, at the same acceleration. So that's inertia. Since we have a light object, it's not going to take much force to really get it moving compared to something that would be really, really heavy that would take a lot of force to get it to move. Okay, so we're going to have 0.0184 newtons of force pushing on our balloon, or somewhere in that ballpark. And again, if your numbers are a little bit different, that's fine. But that's how we calculate. We just take our acceleration and multiply it by this mass of this balloon we've approximated. Okay, so that's for our small balloon. We're also going to do this for our largest balloon in 3 and 4, but the process is going to be the same. So scroll this down here. It looks like basically the same exact problem. But now it's for our bigger balloon. I'm going to use my biggest balloon, the one with the biggest circumference. So for me, that was my trial 5, 32.5 inches. Okay, that traveled 8 meters in 3.23 seconds. So let's go back down here. Okay, so our big balloon also traveled 8 meters. All right, but it took 3.23 seconds to get all the way across. So again, you could do this one of two ways. Either you could take 2 times 8 times divided by 3.23 squared, or you could write it out like this: 2 times 8 divided by 3.23, or whatever your time in seconds was, and then divided by 3.23 again. Okay, so if your calculator doesn't have the exponent button or the squared button, or you're like not sure if you're using it right, this is another way to do it. We're just going to divide by 3.23 twice. That's what that exponent means. We're just repeating that operation twice. So let's try that out. I'm going to switch over back to my calculator. So I'm taking 2 times 8 divided by 3.23, and then divided by 3.23 again. And I get about 1.53-ish. Okay, I can try it the other way too. I can take 2 times 8 divided by, and then divided by 3.23. And then I'm going to put a little exponent on there, make it squared, and I get the same thing. So this 1.53 is going to be our acceleration. So 1.53. And again, the unit is meters per second squared. Now, if I go and compare this, see the acceleration up here, 3.49, 1.53. The small balloon actually accelerates more, which might be kind of counterintuitive to what you might expect. Again, this is the smaller balloon, which has less air. You might think more air means more acceleration and more force, but that's not necessarily true. Again, inertia plays a part in this. A smaller balloon is going to be easier to move around. So even though a larger balloon is going to be still light to us, it is heavier and it has more mass than this smaller balloon here. So it's not going to be as easy to accelerate. Okay, so we end up with a lower acceleration. And you might notice this in the lab that the larger balloon kind of takes a little bit longer to really get going and to pick up speed compared to like a little tiny balloon that just zips right across. Okay, so now we're going to take this acceleration, plug it into our force equation down here, where force is mass times acceleration. So our force, F, is going to be equal to the mass of this big balloon that we've kind of approximated. So again, balloons are kind of hard to measure the mass of on a mass balance or an electronic scale. So instead, I'm just giving it to you. And then we're going to take this 0.01227 kilograms and multiply it by this acceleration here, 1.53-ish. All right, that's meters per second squared. All right, so if we take 0.01227 and multiply it by our acceleration, which is 1.53-ish, we get about 0.0187, or if you round that up, about 0.0188. All right, and the unit for that is newtons. Now, this is something kind of interesting. Our bigger balloon had a slower acceleration, a slower rate of speeding up. Okay, it kind of took a little bit longer for it to get going. But the force on the big balloon is almost the exact same as on the small balloon. Okay, and if you think about it, it kind of makes sense. Even though our big balloon is taking a little bit longer to get moving, that's because it's made of more mass. So whether you have a big balloon or a small balloon, that air can only get out of there so fast. And the air moving out is what causes the reactionary force that pushes the balloon forward. As the air goes out the back, the balloon gets pushed to the front and goes forward. Okay, out kind of towards the other end of where the air is coming out of the open end. Okay, so our air can only escape the balloon so quickly, so that kind of limits how much force we can put on the balloon. Okay, so whether it's a big balloon or a small balloon, whether it accelerates slowly or quickly, whether it's big or small, it kind of winds up having the same amount of force, which is kind of crazy. Now, depending on how your math works out, this might not be exactly the same. You might have quite a big difference in force between one balloon and another, but it just so happens to be that the force on these two balloons was actually pretty darn similar, which is kind of crazy. Okay, so hopefully that was helpful. For future assignments, labs, tests, things like that, we won't really need this equation. So don't feel like you got to commit it to memory or something. We will get more practice with this F equals ma equation. That's going to be very useful to us. And you'll always have that equation available to you. It's just a matter of knowing how to use it.